Hello, we are team A409, and this is our project report. My name is Johan Katukar.
My name is Grant Morrison.
My name is Santiago Garcia,
My name's Ethan Lee.
and we are proud to present our aircraft, the W13G XT.
All right, so we have two stakeholders throughout this project that we've come across, such as the pilot and Reno Air Racing Association. So basically, what the pilot wants is they want a safe and reliable aircraft that they can easily operate while going through the race. Meanwhile, the Reno Air Racing Association wants us to have to follow all the guidelines that they've established, such as the FFA guidelines and stuff like that. Um, and basically, what basically is specifically what the pilot wants is the pilot wants to have structural capability. So to like withstand 6G. So the plane has to like be able to support strong weights. It has to follow FAA guidelines for the association and finishing the takeoff and landing requirements. Some of those are just basic examples of that. And now for the risks, there are around like six risks, which are bad weather, engine failure, birds, structural integrity, and landing wheel issues. So for the bad weather part, like basically weather can come in and affect it can affect basically the pilot's visibility. It can affect like how the engine works or anything like that. Engine failure can happen mid-flight when the engine just decides to stop working as a whole, and then the plane may have to take down, or in worst cases, it might crash. For birds can collide with like very important parts of the plane, such as the engine, the turbine, and it can basically stop them from working if it collides with them and provides a significant amount of force that causes it to just no longer work as a whole. For structural integrity, the plane can sometimes just like fall apart, like the wings can fall apart meanwhile mid-flight or anything else like that. And landing wheel issues are like issues as in like the plane's landing wheels do not extend or retract fully, which can create a problem for the plane when it wants to take off or land.
All right, so I'll be going over the calculation process we took to arrive to our final aircraft design. First, we chose a reference aircraft, and the reference aircraft of choice was the P-51D Mustang, which is shown here. The P-51D's high-speed, low-altitude performance capabilities, as well as its low-drag configuration, made it the perfect choice for our project. In addition, the P-51D is among one of the most well-documented aircraft, so researching the various parameters was very easy. So once we were able to attain the P-51D's values, we were able to use them to estimate our initial gross takeoff weight. And from this calculation, we were able to calculate wing loading. Then from wing loading calculations, we were able to use it in association with our gross takeoff weight calculations to find the dimensions of our aircraft. And from the dimensions, we were able to arrive at a NACA. So the NACA airfoil of choice for their wings was the NACA 2412. Um, and we arrived at two different tail airfoils. The NACA 12 was selected for our vertical tail, while the NACA 10 was selected for our horizontal tail. The NACA 12 was selected for the vertical tail as it had to sustain more structural loads, while the NACA 10 was settled on for the horizontal as it is susceptible to less loads.
After calculating all of these values and selecting other ones, we came up with three different concept aircraft with different variations. For example, we looked at different wing placements. We looked at a high wing aircraft versus a low wing aircraft, and we also analyzed different types of landing gear. So, tricycle landing gear, the tail dragger, and then retractable landing gear. We also analyzed the placement of the horizontal stabilizer. For example, we analyzed a T-tail versus a conventional tail. And another one of the important modifications that we made was the cockpit placement, because we had to consider how the pitching moment of the cockpit positioning would affect the aircraft balance overall when taking into account the heavy engine.
And through all that, we reached our final design, which incorporated tapered wings, a cockpit placement behind the wings for more weight distribution because we used the Merlin engine, which is placed at the front of the cockpit, and that results the center of gravity to be more towards the front. So we decided to put the cockpit behind the wing to even out that balance. And then we decided to go with retractable landing gear for more aerodynamic efficiency. We chose tapered wings because of the structural and maneuverability is more efficient than elliptical wings or other wing styles, and it allows it to be fast and competitive in the race. Through the airfoil, we got our NACA 2412. We found our CD0 when graphing the CL and CD chart. So we got a CD0 value of around 0.012. And through that, we could plot our drag polar and our linearized polar graph, as well as through other calculations, found our power required and thrust required versus available. And then we could also find the lift to drag ratio max LD at the specific speed, which is around 17.42. And then over here, we have our max rate of climb versus the altitude. And here are some main takeaways that we have.
So during the development of this project, we faced several challenges that required us to change our approach and refine our engineering judgment. A very clear example of this was when we started with our sizing code, we realized very quickly that the coefficients that we were using that were based on the book Raymer Chapter 3 were outdated and didn't really apply to racing aircraft. So we had to go through our code, analyze how each coefficient affected our outputs, and then look for new coefficients that were applicable and then find a justification for using them. Another very important thing that we learned was the importance of making informed trade-offs. For example, when choosing a NACA, you have to decide between having a more aerodynamic and more efficient NACA and having more structural integrity. So we had to analyze the G loads required for the aircraft versus the aerodynamic efficiency. And we basically had to make trade-offs like this for every single component of the aircraft. And so after this thorough performance analysis of the aircraft, we found that our aircraft does meet all the necessary requirements for the unlimited class air race. And we believe our aircraft would successfully complete the mission. Thank you.
Thank you.
Thank you.